In this lecture part, I will talk about observations of solar wind. Solar wind observations are essential to understand the properties of the sun, the solar wind from its origin to up to about 1 AU or beyond actually. In this lecture, I will cover some part of formation of the solar wind and how the solar wind is getting accelerated from the sun and the radial evolution of the solar wind. Solar wind changes as it originates from the surface of the sun to a large distance from the sun. That radial evolution we will see, and we will see the how the solar wind is varying in 3-dimensional phase, and that solar wind variation in 3-dimensional space also has solar cycle changes. So, I assume that you have some idea about the solar cycle and solar activity variation and things like that. And we will also see some part of transient solar wind. For example, there are several activity taking place on the sun, like solar flares, coronal mass ejection, and the high speed stream propagating away from the sun. They interact with low speed wind in the interplanetary space. They cause co-rotating interaction regions. So, these properties of this solar wind transients also we will see. To start with, let us see the formation of the solar wind. Okay. The concept of continuous solar wind was developed in 1950s. For example, 1951 to 57, Biermann observed comet tails as they passed close to the sun and explained the observed tail deflection by a continuous flux of protons from the sun. For example, as a comet goes close to the sun, the length of the tail increases. So, you can see in this video, as the comet passes close to the sun, the tail size increases. So, he postulated there must be some continuous flow of protons from the sun. 1958, Parker postulated the continuous expansion of the solar corona, that is outward streaming of corona gas, and it was named as solar wind. For example, this video gives just some view of solar wind as the comet Hyakutake went close to the sun. Okay. The formation of the solar wind is governed by 3 equations actually. For a steady state of spherically symmetric solar wind, equation of motion, equation of continuity, and energy equation. If you understand this, then the solar wind flow can be easily understood. For example, equation of motion deals with for example, this part deals with the gravitational energy and thermal energy and kinetic energy. So, when there is no solar wind flow, the equation of motion gives the steady corona or steady surface. The equation of continuity, that is governed by density and speed as a function of distance from the surface of the sun, and energy equation, which has thermal energy, kinetic energy, and gravitational energy. So, they give the bound solution for the solar wind flow actually. For example, there is another term. This was proposed by Parker in 1958, the radial variation of solar wind. For example, r to the power of minus b when b is much smaller than 1. For example, at the base of the corona, B is much less than 1, it is about 0.3. Okay. For example, E becomes greater than 0 at about 10 solar radii actually. So, E is less than 0 within 10 solar radii. So, there is no formation of the solar wind. So, for example, these three equation governs the solar wind flow. Let us see, B is negative, at the base of the corona the system is stable. Gravitational potential decreases as 1 over r, and thermal energy is governed by T as a function of r, which is a weak function of distance r. For B about 0.3, E is greater than 0 at about 10 solar radii. For example, in this equation, the energy E equal to thermal energy plus kinetic energy plus gravitational energy. This equation gives energy less than 0 for distances less than 10 solar radii, but at about 10 solar radii E becomes positive, then solar wind flows with supersonic speed. And for example, gravity supports as the nozzle flow, like a rocket jet, the solar wind flows. But we know now lot of observations and other theoretical studies explain that thermal energy alone cannot explain the solar wind speed near the sun and beyond. Actually. So, we will see some of the parts. So, the basic idea about the solar wind flow is the thermal part of the solar wind overtakes the gravitational flow, and that aids to formation of the solar wind. Okay, let us see the properties of the solar wind. It is a supersonic outflow into interplanetary space. It is made of plasma from solar corona, and solar wind is composed of approximately equal number of ions and electrons. Ion component consists of predominantly proton, something like 95%, with a small amount of doubly ionized helium and trace amount of heavy ions actually. So, the solar wind, when it flows from the corona, it carries the solar magnetic field known as interplanetary magnetic field. So, and solar wind properties like density, velocity, temperature and magnetic field varies with solar cycle. It has a it varies with approximately 11-year solar cycle, and we see solar wind properties varying with heliographic latitude as you go from equatorial region of the sun to polar region in the north pole, or equatorial region of the sun to the south pole. So, we see solar wind properties varying, and also solar wind properties varies with with the heliocentric distance. As you go away from the sun, the solar wind properties change, and also the solar wind also vary with rotational period of the sun. Sun has a 27-day rotation period, and it has a rotational period variation that is mainly due to source region located on the sun. If several active regions are on the sun, so you get a solar wind with active region properties. If you have several coronal holes on the sun, mid latitude coronal holes, so the coronal hole properties are reflected on the solar wind. Sometime you see a blank disk, so the solar wind properties are dominated by blank region on the sun. So, the solar wind can vary with a solar cycle variation. So at or we can say solar wind can vary in all time scales, and also it can have a three-dimensional view. Also, solar wind varies in response to shock waves and turbulence that perturb the interplanetary space. So, as the solar wind flow from sun to earth or beyond, so it can cause shock waves, and the turbulence level also can vary. So, these things are also gets embedded in the solar wind. So, if you see the average properties of the solar wind at about 1 AU near the earth orbit, the velocity is something like 470 kilometer per second, and density is something like 9 proton per cc, and magnetic field strength is something like 7 nanotesla. This is the typical density, velocity and magnetic field at near earth space. So, if you extrapolate it to something like you want to study solar wind at about 10 AU, or you want to study solar wind at above at the edge of the solar system, these numbers will vary, but typically the solar wind speed does not vary drastically with distance from the sun. The drastic variation is seen within about 20 solar radii. After that, the solar wind speed variation is typically very small as we go away from the sun, whereas the density, it can have a 1 over r square dependence, and also magnetic field can also have a radial dependence. Okay. So, the heliosphere and solar wind studies involves exploring heliosphere in three-dimensional space. So, as I told, the acceleration of the solar wind from the solar surface to outer distance, how the solar wind is getting accelerated from something like 0 velocity, from the thermal velocity to supersonic speed, how it is getting, and how the generation of high speed streams with the given speed, density and temperature, how do they originate, and coronal propagation of solar energetic particles. Apart from solar wind, sometimes high speed streaming particles will be originating from the sun. So, the coronal propagation of high speed energetic particle and the solar transients, for example, coronal mass ejection, CME. Okay. How do they originate, and what is their trajectory, or what is their propagation path? So, and also large scale variation of solar wind and magnetic field and the behavior in the interplanetary space. For example, large scale variation of solar wind, magnetic field and turbulence level in the varying distance from the sun, as well as from the sun as a function of solar cycle. So, these are all the important studies one need to do to understand the global properties of the solar wind. Okay, this picture shows the picture of the corona during solar maximum. Actually, so you can see during solar maximum, the corona is somewhat symmetric with respect to the south to north pole, and so the central picture is extreme ultraviolet image and embedded with the EIT corona. Okay. So, you can see the previous picture shows the corona during the solar minimum. So, for example, if you see the minimum corona, so you see open field configuration on the solar north pole as well as south pole. So, the corona looks somewhat something like ellipsoid shape actually. So, whereas in the maximum corona we see we see spherically, nearly spherically symmetric solar wind in between solar activity. So, for example, in the ascending phase or in the descending phase of the solar cycle, if you see, so the corona is dominated by closed field region as well as open field region. This picture taken from Kundausan, it shows the typical coronal shape or coronal magnetic field shape during the ascending phase of the solar cycle or descending phase of the solar cycle. So, the corona itself changes something like nearly spherically symmetric at the maximum phase to some kind of ellipsoidal shape to the minimum. So, in between we see varying structures of the corona. Okay. So, for example, this is a Yoko soft X-ray picture of the corona and taken during close to the minimum. So, the dark region on this picture shows the coronal hole actually, because X-ray emission is less from the coronal hole region. So, we can see the dark region. The bright regions are the active regions. As you see, the dark region are less X-ray emitting region on the north pole side of the sun is the coronal hole. So, it involves open field configuration. From the coronal hole, the magnetic field is opening outward, whereas the active regions in the mid latitude region, we see active regions which are close to the field region, and then so we have some findings that near the close to the field region the slow solar wind originate actually. So, the high speed winds are from the coronal hole region. Sometimes high speed transient can takes place from the sun, like coronal mass ejection. So, they can have a very huge speed, something like so we saw the average speed of the solar wind at 1 AU is something like 470 kilometer, but the typically the speed from the coronal holes are about 800 kilometer per second, and speed from the closed regions can be something like 250 to 400 kilometer per second. But the coronal mass ejection can have a varying speed. So, they can be pushed into the interplanetary space something like 100 kilometer per second to something like 4,000 kilometer per second. So, they are the transients, they have a huge varying speed. So, this shows the typical interplanetary magnetic field because the sun has the rotation, the solar wind is pulling out the magnetic field from the sun. So, because of the rotation and pulling out speed, so the magnetic field gets dragged like a Archimedean spiral. So, they are known as Parker spiral also. So, this is the typical Parker spiral for solar wind speed of the order of something like 400 kilometer per second. For example, the Parker spiral curvature can change depending upon the solar wind speed. For example, 800 kilometer, the curvature will be less, the solar wind will be pulled nearly radially outward. Something like 2000 kilometer coronal mass ejection is flowing out with a speed of 2000 kilometer per second. So, the spiral can have a nearly a straight line shape. So, the low speed solar wind, they form a large curving magnetic field line, and high speed solar wind. So, they form less curving magnetic field lines. So, this is the interplanetary magnetic field. The circle shows the orbit of the earth. So, we can view at the orbit of the Earth how the solar magnetic fields or interplanetary magnetic fields are oriented actually. So, actually this picture shows the red curve is for 400 kilometer per second, and then the yellow curves are for 2000 kilometer per second. So, we can see the varying curving of the interplanetary magnetic field actually. Okay. So, yeah, as I told, if a coronal mass ejection CME is flowing out, how it drags the magnetic field from sun to earth or beyond actually. Yeah. So, since the originating solar wind has a magnetic configuration embedded with it. So, as the solar wind flows out from sun to large distances, 1 AU or 10 AU, the magnetic current sheet actually the current sheet between two polarities, positive and negative polarity, or south polarity and north polarity. So, they also propagate from the sun to earth. So, this shows the typical current sheet with respect to the center of the sun to about 1 AU actually. So, this gives the warping of the current sheet as we magnetic current sheet as we go from sun to earth distance actually. Okay, so the solar wind properties can be divided into two groups: steady state solar wind, and its origin and acceleration is important. So, they involve low speed solar wind as well as high speed solar wind associated with coronal holes, and the disturbed solar wind I have been mentioning actually, the coronal mass ejection, solar flare and the interaction regions. So, they cause disturbed solar wind. So, let us see the typical properties of steady state solar wind, its origin and acceleration. Okay. So, here this table gives the typical properties of the solar wind, okay, for the low speed wind as well as high speed wind. So, the low speed wind, the typical speed is less than 400 kilometer, and density can vary from something like density can vary from 5 to 10 particle per cc, and they have a filamentary structure, and also the proton temperature and electron temperature. So, they also have a variation. So, they are associated with plus minus 30 degree latitude, the source region on the sun, and they are observed in all latitude during solar maximum. Solar minimum, they are confined to the equatorial region of the sun, and solar maximum we see at all latitudes. So, the corona itself becomes spherically symmetric, whereas high speed spin, the high speed wind, they originate from coronal holes. The speed can be of the order of something like 600 to 800 kilometer per second, and the density is something like 3 particle per cc. So, you can see the low speed wind has a high density, and high speed wind has a low density. So, they have a uniform structure, and typically the proton to electron temperature varies by 2 times, and during solar minimum they are associated with the polar region of the sun. So, they originate from the polar region, whereas during solar minimum during solar maximum they can be originating from low latitude coronal holes actually. So, these two difference gives the typical properties of the major property difference is seen in speed, density, and proton temperature. One can see actually proton temperature can be one order difference, and speed can be 2 times, and then the density can be 2 to 3 times difference actually. Okay. So, this plot shows the x-axis shows the solar offset, goes from a near sun region to something like 1 AU. So, 214 solar radii is 1 AU. So, it goes up to about 1 AU. In the y-axis, the vertical axis, we have a temperature. So, as we go away from the sun, okay, how the proton temperature and the electron temperature decreases with the distance. So, you can see the electron temperature is not varying drastically as we move away from the sun, whereas the proton temperature decreases rather quickly. So this graph also shows actually this thing, density and electron temperature, and then mean free path as we go away from the sun. Near the chromosphere, it's the density is something like 10 to the power of 10 per cc, and at about 1 solar radii, the temperature is this thing 1000 times lower than the chromospheric temperature. At about 1 AU, the density falls off by million times. Okay. So this is the typical density variation, whereas electron temperature, if you take in the this thing, there is a from chromosphere to corona, there is a huge increase in temperature, which is due to the coronal heating, and something like million degree temperature falls to something like 100,000 degree at about 1 AU. So the electron temperature variation is rather gradual, whereas the mean free path, it goes from something like 10 kilometer to 10 million kilometer at about 1 second. So the mean free path is huge as we go away from the sun. So okay. So this plot shows the typical variation of speed, density, and speed for one solar rotation actually. So the x-axis is the day number. It's for typically 30 days. So we can see the thermal speed of the solar wind. So which is typically goes from something like 25 kilometer to 130 kilometer, and we can see the density variation, which is varying from something like less than a particle per cc to something like 50 particle per cc, and the speed goes from something 300 kilometer to 800 kilometer. So the 800 kilometer speed is associated with coronal hole region. So if you compare the speed and density, you can see a decrease in density when the speed is high. So that indicates the typical properties of the coronal hole. Okay, how the solar wind can be measured actually. Okay, so at near Earth space, that is at about 1 AU, the solar wind properties are from in situ measurement. That's use spacecraft and satellite to measure solar wind speed. And for example, in between sun and earth, is there any other method to measure the solar wind speed? So interplanetary scintillation technique is used to infer the properties of the solar wind in the distance from sun to earth distance, and also in situ measurement or point measurements. They give properties of the solar wind at a given point. So in situ measurements, it's very difficult with the in situ measurement. It's very difficult to get the three-dimensional view of the solar wind. For example, most of the satellites, they are confined to ecliptic plane at about 1 AU. So, Ulysses was the first spacecraft to probe the polar region of the sun, and also Ulysses distance was something like 1.5 AU to 5 AU, and the Helios satellite measured solar wind up to about 0.3 AU. So, the Helios could go as close as 0.3 AU from the sun. So, all other spacecraft, they are confined to 1 AU, and they are confined to ecliptic plane or equatorial region of the solar wind. But whereas the remote sensing technique like interplanetary scintillation, they can give a three-dimensional view of the solar wind at sun earth distance at all latitude, and they are useful to study the long term variation and large scale structure of the solar wind. But one limitation with the interplanetary scintillation kind of remote sensing technique is they are line of sight integration measurement. There are some methods to remove the line of sights. So, we will see some of them in the later part of the lecture. So, the solar wind acceleration. So, how the solar wind is getting accelerated from sun to about 10 or 20 solar radii actually. So, this plot shows the speed variation from sun to earth orbit actually. So, how the solar wind speed is increasing from near sun region to at about 20 solar radii and beyond, and how the other properties are also changing. So, we will see this plot in detail. Okay. So, for example, if you take the thermal energy alone, sun temperature or coronal temperature alone, how much they can account or they can contribute. For example, V thermal is decided by the KT, where T is the temperature of the corona. So, V thermal is of the order of 130 kilometer per second in the near sun region. But we know that the solar wind speed is something like 400 to 800 kilometer per second actually. So, what are the other factors involved in the solar wind acceleration? Okay. So, the magnetic field expansion factor also plays a crucial role in aiding or supporting the solar wind acceleration. For example, so this shows the typical magnetic field from the photosphere to about source surface, okay, where the source surface can be fixed at about 20 solar radii. So, the magnetic field this thing expansion factor, that is the area on the photosphere to area under the on the source surface. So, AS divided by A photosphere gives the typical expansion factor. Is this expansion factor of the magnetic field plays a crucial role in the acceleration of the solar wind? Let us see how the expansion factor is varying. For example, smaller expansion factor corresponds to a low speed wind actually. Okay. Smaller expansion factors corresponds to high speed wind, whereas a larger expansion they corresponds to low speed wind, or the binding of the magnetic flux line is regular, or if the binding is very good for a larger distance, they involve high speed wind. If the binding becomes loose and then if the magnetic field expands rather largely, they involve low speed wind. So, this study can be seen in Wang and Slee 1990 paper. So, this is known as the Wang and Slee model actually. Okay. For example, here the expansion rate less than about 0.3 gives a velocity greater than 6.5, and the expansion factor something like 3 to 9 gives 650 to 550 kilometer, and the expansion factor greater than 18 gives less than 450 kilometer. So, the expansion factor is the factor on the base of the sun or on the photosphere to at about 20 solar radii above the sun actually. So, if this magnetic field is showing huge divergence, so they involve low speed wind. So, the magnetic field plays a crucial role in accelerating the solar wind. First of all, the thermal part, and then the magnetic field expansion plays a role. So, here the x axis shows the year, and then on the vertical axis we have the solar wind speed. So, they are from in situ measurements. So, we can see the dotted lines are in situ measurement, and then the continuous line shows the expansion factor corresponding to the in situ observation. So, you can see the expansion factor and then the solar wind speed, they follow one to one correspondence. So, it gives a clue that expansion factor plays a major role actually. So, in this curve the shows the horizontal axis is the magnetic heliographic latitude in degrees, and then the vertical axis is the solar wind speed, and this is for North Pole and South Pole. We have that this thing magnetic latitude. Okay. So, the solid curve is for north, and in the bottom solid curve is for the north, and the dotted line is for the south, and then we have the expansion factor. Okay. So, as the expansion factor decreases, the solar wind speed increases actually. Okay. So, this is from Goldstein 1995 study. So, we have a clear idea now. The magnetic expansion factor plays a major role in formation of the solar wind. Okay. So, this study is from the interplanetary scintillation measurements. So, the bottom plane shows the photospheric magnetic field. The magnetic fields have been obtained from extrapolation of the magnetic field. It is for one solar rotation, and then the bottom the top plate shows the solar wind speed. So, the low speed wind originate close to the or at the edge of the closed magnetic field region, where the expansion factor is very high actually. So, the closed field region expansion factor is very high. So, they lead to low speed wind. So, a couple of studies using the interplanetary scintillation has given the origin of slow speed wind, which is linked to the expansion factor. So, I will show the another example. So, for example, this curve shows the velocity as a function of 1 over expansion factor, and then this shows the velocity as a function of magnetic field intensity. This one shows the velocity as a function of magnetic field and expansion factor. So, we can see a good correlation with the B over F nicely correlate with the speed of the solar wind. So, the expansion factor alone cannot decide the speed, magnetic field alone cannot decide the speed, but magnetic field combined with the expansion factor could give a good correlation with the solar wind speed. So, the bottom line is the solar wind acceleration or the solar wind speed is coupled to the thermal energy. solar wind speed is coupled to the magnetic field on the sun, and then the solar wind speed is coupled to the how the magnetic field varies from the surface of the sun, how fast it is expanding. So, if the expansion is quicker, then they lead to slow speed wind. If the expansion is rather slow and the expansion factor is small, they lead to high speed wind. These plots shows this thing, how the high speed wind originate above the open field configuration actually. So, this work was done by Martian Tew, and this well known established work for high speed wind flowing from the coronal hole region actually. Okay, so this plot shows in the x axis we see the distance from the sun, and then again the y axis we see. So, we see a acceleration of the solar wind as a function as we go from something like 1 solar radii to 10 solar radii, but for a given distance we see a large variation in solar wind speed also. For example, here we see high speed wind at about 10 or 15 solar radii, so possibly enhanced by wave motion, and then we see large variation at a given something like 30 solar radii, we see large scattering or for a given distance we see large. So, these things can be due to properties associated with the region on the sun. This work is from we did it combining scintillation and other theory, we did this work actually. Okay, the radial dependence of the solar wind. So, so far we saw the origin of the solar wind. So, origin, thermal energy plays a major role, magnetic energy plays a major role, and then the magnetic field, how they evolve with distance from the sun, they also play a major role. How rapidly solar wind this thing accelerated, and then they reach the final speed actually. Okay. So, for example, we see the expansion factor, and then the estimated this thing continuity equation also plays actually. So, let us see the three-dimensional view of the solar wind. Okay. So, three-dimensional view, how the solar wind this thing seen in 3 dimension. So, these plots, the top plots are for the density turbulence, and then bottom plots are for solar wind speed. So, and in the top plot, the middle we see a low density turbulence region, and then so that is associated with the small coronal hole. So, whereas in the bottom plot the same region is associated with the high speed wind. So, this plot covers something like 180 degree on the heliosphere. So, each plot is taken at about 100 solar radii away from the sun. These plots are from interplanetary scintillation observation from Ooty, and this is midway between sun and earth, where no spacecraft or no other observing means are there to observe solar wind at about 0.5 AU away from the sun. So, this is 3 days. Okay. So, 3 consecutive days, how the solar wind density is varying, and then the bottom plot shows how the solar wind speed is varying. So, in the 3 dimension, solar wind has large structures. So, you can see small structures to large structures in the heliosphere. This is something like 200 solar radii diameter heliosphere actually. Okay, so this plot shows the solar wind density turbulence and solar wind speed. The bottom plot is for the speed, the top plot is for the solar wind density turbulence. So, this covers approximately something like 60 days actually. So, March and April. Okay. So, the density turbulence, so this goes from south pole to the north pole, similarly south pole to the north pole. So, within 60 days the solar wind has a large structures actually. So, the top plot shows this thing, polar regions are dominated by low speed low density turbulence, and then mid latitude is covered by high density turbulence. Similarly, here the north pole and south pole, they are dominated by high speed, and then mid latitude or low latitude regions are dominated by the low speed. So, this is the typical configuration for the solar minimum actually. Okay. So, for example, this plot is for 3 days, this plot is for something like 60 days, 2-month period. So, this plot shows how the solar wind varies with heliographic latitude from the in situ Ulysses measurement. So, this one is for the solar maximum, the other one is for solar minimum. So, with the maximum to minimum, we could see the solar wind speed variation as a function of heliographic latitude. Okay. So, again solar minimum, okay, this is for solar minimum cycle 22, this is from UT interplanetary scintillation measurement, and here we see the north pole and south pole, they are dominated by high speed, and the equatorial region, they are dominated by the low speed. The white line indicates the magnetic current sheet in the heliosphere. Again, this plot is between sun and earth distance. Okay, so we know the sun is varying, sun activity is varying every 11 years. So, it goes from solar minimum to maximum, again minimum, maximum. So, this shows the sunspot number as a function of year for something like 3.5 solar cycle. Okay. So, this plot shows the magnetic field on the photosphere, how the blue magnetic field moves from one polar region to the other polar region. Similarly, the yellow moves from one polar region to the other polar region. So, the magnetic polarity reversal takes place. So, in this period, so how the solar wind density varies. If you see this shows for something like 1988 to 2015, the density turbulence as a function of heliographic latitude minus 90 degree to plus 90 degree. These plots are from interplanetary scintillation observations from UT, and they are made at about 0.5 AU from the sun. So, you can see one solar cycle to the other solar cycle, there is huge difference in density variation. For example, cycle 22 was dominated by high density, and the cycle 24 was dominated by the low density. So, this shows the solar wind speed. Okay. So, if you compare the solar wind speed and density turbulence, so they have one-to-one anti-correlation, but the structures are different. So, the three-dimensional view of the solar wind shows a drastic variation from one solar cycle to the other solar cycle. And also you can see in the current solar cycle, we see a polarity reversal taken place in the south pole, whereas in the north pole the polarity reversal is still going on. So, that so the solar wind study can give information about the activity magnetic field associated with each activity cycle. Okay. So, now let us see how the transients they vary from from sun to earth, because the radial evolution of coronal mass ejection, they are of great importance, because the coronal mass ejections, they produce severe magnetic storm at the earth magnetosphere. So their arrival, their properties are to be known well in advance to protect near earth satellite, and for other technological reason also. So predicting their arrivals are important, and also predicting their arrival means one has to understand the radial evolution of coronal mass ejection from sun to earth, actually, for example. So this gives some of the images of coronal mass ejection made using the UT radio telescope. Here the red color indicates the background solar wind, and then the enhanced color indicates the presence of coronal mass ejection. So this is from sun to 1 A distance. So this each plot is 2 AU diameter plot. So one can see the propagation of coronal mass ejection. So for example, so the UT gave a very good understanding about the evolution of the coronal mass ejection as it goes from the sun to earth. So each plot, how the speed is varying. So high speed is coronal mass ejection, which is originating from at about something like 2,500 kilometer. They this thing decelerate rather quickly at the earth orbit, actually, whereas some coronal mass they get accelerated, some move with a constant speed. So this gives the idea when the coronal mass ejection is moving in the interplanetary medium, when the coronal mass ejection is propagating in the interplanetary medium, they exchange energy with the ambient solar wind. So the exchange of energy they go through a drag in the ambient solar wind. So the drag causes the coronal mass ejection speed to decrease. So when we tracked several coronal mass ejections from sun to earth, we understood what kind of drag force can be playing a role in shaping the speed profile of coronal mass ejection. So those results came from UT radio telescope, and so these are some. So actually this gives the efficiency of momentum transfer is determined by the drag force and ram force. So this gives a typical idea about this thing. Several other authors have studied the drag effective. So for example, Manoharan et al., Gopalswamy et al., Gargil, and Prasad and Versenak, Lindsay, Lara, they all studied the drag imposed on CMEs due to the ambient solar wind. So that plays an important role in shaping the speed profile of the coronal mass ejection. Okay, now interplanetary scintillation at UT we can observe in a day more than 1,000 radio sources. Okay, which is huge in number. It's a good record, actually. So in a solar rotation, we can have a 30,000 lines of sight. So this shows the typical lines of sight observed, because each line is the observation from earth to the source. So this gives the typical lines of sight observed in one solar rotation, about a 27-day period. So since we have large number of cuts in the heliosphere, we can do a computer assisted tomography to understand the three-dimensional heliosphere also. It's a typical tomographic analysis. The tomograph for interplanetary scintillation observation, UCSD, University of California at San Diego, they developed a tomography software. We used that software to reconstruct the three-dimensional heliosphere using IPS observations from Ooty. So, for example, this shows the ecliptic view of solar wind density and speed reconstructed from the Ooty observation. So, the orange plot shows the density, and the blue plot shows the velocity for about one solar rotation. So, the diameter of this field is 3 AU. So, you can see small density structure moving away from the sun, how they moving along the Parker spiral. So, those things can be seen. The concentrated density, they give the idea about the moving coronal mass ejection. Similarly, in velocity also, the intense dark region indicate the high speed wind, and the light region indicates the low speed wind. So, we could see the how the velocity is varying in the 3-dimensional space. So, this is the 3-dimensional view of density turbulence or density obtained from the Ooty measurements. So, here in this plot, the circle indicates the orbit of the Earth, and then the blue globe indicates the position of the Earth. With respect to the Earth, how the density structures are moving. For example, you can see in this movie, you can see a big flux rope. Yeah, you can see this one. Yeah, the flux rope coming out of the sun and moving away. So here the flux rope is associated with the expanding magnetic cloud actually. So, you can see the toroidal expansion versus the poloidal expansion. So, how different the toroidal and poloidal expansion. So, this shows the dynamic heliosphere. As we think, the 3 AU heliosphere seems to be dynamically varying in time scale. This gives something like 25 days how the heliosphere is varying. So, this is the typical example of how the solar wind dynamics is varying in the 3-dimensional space. So, the concentrated density regions are associated with the warping of the magnetic current sheet actually. Yeah. Okay, this shows the typical properties of the solar wind associated with the transient as a function of day number. This is for 2015 even. This gives us something like a 10-day period, and then magnetic field, interplanetary magnetic field, and then speed, density, temperature, and 10 MeV proton flux, and then DST index actually. So in this plot you can see something like 6 interplanetary shock arriving in the near Earth space actually. So at 1 AU the observation of solar wind indicates several important properties like arrival of the shock, arrival of the CME, and also in association with the arrival of the CME, how the geomagnetic storm is produced and things like that. So, okay. So again, so this plots gives some more examples. This is the x-axis is the day number, and then y-axis we have plotted the magnetic field latitude, longitude, temperature, and then oxygen ions, and then this thing abundances actually. So this gives the how the coronal mass ejection arrival is associated with the arrival of the shock, and then within the coronal mass ejection how the magnetic field variation, okay, that is the magnetic cloud, how that properties can be seen actually. Yeah. The co-rotating interaction. So we saw some properties of ambient solar wind, how they are accelerated, and then we saw some properties of coronal mass ejection coming from the sun. Now co-rotating interaction region, how they are formed actually. So, the chorotic interaction region, the high speed wind, for example, here the yellow color lines are associated with the high speed wind, the red color lines are associated with the low speed wind. So, since the high speed wind interact with the low speed wind, at the interaction region sometime we get shock actually. So, when the high speed wind interact with the low speed wind, here the high speed wind interact with the low speed wind. So, they can produce shock and they can produce also geomagnetic storm. So, the number of interaction region seen in a solar cycle can be large in number. They are also important in terms of geomagnetic activities as well as the space weather applications actually. So, here in this three dimensional reconstruction, again this is from the Ooty observation. Okay. So, you can see the high speed streams coming out of the sun, and then so you can see a very big high speed stream, and then their interaction with the ambient solar wind. So, this Carrington rotation, this 27-day period of the sun was dominated by high speed wind. This happened in 2008, close to the peculiar solar minimum actually. Yeah. So, more open question: how does the magnetic field in the solar wind region connect to the photosphere and the heliosphere actually? So, there are, because we understand the origin of the solar wind, still there are several open questions actually. The magnetic field connection from the photosphere to the heliosphere. How do the observed structure of the corona evolve in the solar wind? So, we observe some structure on the corona. As we go out, or as the corona sense the solar wind, or as the corona sense the coronal mass ejection, how do they evolve in the solar wind? So, does the solar wind preserve the coronal properties to large distance from the sun? So, that is another question. Is the source of the solar wind steady or intermittent actually? So, one low speed solar wind source is there. Does it live for longer time or considerably longer time, or are they intermittent? So, some of these questions need to be answered actually. So, the understanding the life structure of solar wind source region. How do the process in the corona affect the properties of the heliosphere? For example, now a number of researchers, they try to connect the properties of the corona with the properties of the solar wind. How do the process of the corona affect the properties of the solar wind? Or one can put, is there a link between the heating process in the corona and the solar wind? Next, what mechanism accelerate and transport energetic particle from the sun to earth? Because we have not seen the energetic particle, because energetic particle can be high speed streaming particle. Okay. What causes them to transport from coronal origin to near earth space or beyond? Okay. So, sometime the particle event can be gradual event, or sometime particle event can be a impulsive event. So, impulsive event means sudden increase in particle flux, and then this thing. Gradual event means they keep on accelerating the particle for even for a couple of days also. Okay. So, these are all the open questions. Okay. So, the understanding the heliosphere structure, so involves how do coronal structure evolve into solar wind. Okay. Varying speed, density, kinetic temperature, composition and magnetic field. How do CME driven disturbance evolve in space and time as they propagate in the inner heliosphere? That is another open question. What is the structure of IMF at very large distance from the sun? Okay, very large distance from the sun. So, we saw the IMF, curving of IMF and decreasing of IMF as we go from sun to earth, but what is the structure of the IMF at a very large distance from the sun? So, that is another one. how are plasma, neutral, heavy ions and turbulent fluctuation and SCP and galactic cosmic ray distributed in the heliosphere actually. So one topic we did not touch upon, the interplanetary magnetic field plays a major role in controlling the galactic cosmic ray entering the Earth atmosphere. So, how the this thing galactic cosmic ray variation vary with solar cycle or vary with in association with interplanetary magnetic field associated with the coronal mass ejection or interplanetary magnetic field associated with the interaction regions are also. So, interaction of solar atmosphere with the local interstellar medium is another open question. Nature of local interstellar medium and its counteraction to the solar wind is another important subject. So, okay. So, this because solar wind itself is a huge subject, but it can be carried to up to the edge of the solar system and its properties with other processes happening in the edge of the solar system can be studied.